Hello everybody, my name is Satoshi Hoshino. I'm from Utsunoe University, Japan. Today I'm going to talk about aerial surveillance system with multiple agents for moving targets. Okay, so first off, as you can see here in this simulation movie, we have so many aircrafts in our airspace. Many of the aircrafts are equipped with a so-called ADSB, Automatic Dependent Surveillance Broadcast for Identification. However, 30% of all the aircrafts are not equipped with the ADSB or the ADSB is broken. Because we cannot identify such aircrafts, these aircrafts have negative impacts on the air traffic. For this issue, we focus on aerial surveillance systems in this presentation. Okay, in our surveillance system, one sentinel and multiple searchers are used as illustrated in this figure. The sentinel here hovers in the same place and the searchers move to approach the target. So in order for the searchers to identify moving targets as many as possible, it is required to solve the following challenges. First off, we have to estimate the feature positions of a target. In addition, searchers are required to approach the target efficiently. For the first challenge, we use von Mises circular distribution, and for the second challenge, we use a value iteration method in order to optimize the approach behavior of searchers. For the first challenge, the target motion monitored by the sentinel is quantitatively expressed on the basis of the von Mises distribution. The von Mises distribution has a circular shape, thus the probability density is defined along the circle of a monitoring area as shown in this figure. In the surveillance system, the monitoring area is divided into cells. So the target moves toward a destination cell. The blue cells corresponding to the edge of the monitoring area are candidate cells for the destinations. For the candidate cells, the moving direction of the target is expressed by the probability density function of the von Mises distribution, as you can see here in this equation. Each time a target is monitored, the probability density of the von Mises distribution is calculated from this equation. So as you can see here in this figure, a target is now moving toward in this direction. So for each of the candidate cells, the probability density is drawn by a red bar, as you can see here, okay? The probability densities in the cells are used for estimating the feature positions of the target. For an unknown destination of the target, we first assume a destination cell, which is theta eta, okay? And at time t, the current position of the target is represented by xt. The moving probability of the target from xt to xt plus 1 at time t is formulated as follows, as you can see here. This equation is first based on a probabilistic dynamics model. And as you can see here, in the last factor, the probability density function is additionally used in this model. So as a result, the moving probability of the target is calculated in consideration of the moving direction, even in the aerial environment. Here, the parameter theta represent a set of the candidate cells for destination. So this calculation is repeated for all the candidate cells, okay? And here, a probability P is derived directly from this equation, okay? And this probability P is calculated using Bayes' theorem, given a series of the monitored positions, okay? After the calculation for all the candidate cells, the moving probability in each cell is averaged. For the averaged moving probabilities within a set of xt plus 1, which are reachable cells from the current position xt in one step, as you can see here. Okay. a cell with the maximum moving probability is estimated as the next position of the target, x hat t plus 1. As you can see here in this figure, the cell with this red dot has the maximum moving probability. So this cell is an estimated next position of the target, which is x hat t plus 1. Okay. On the basis of this estimation, on the basis of this estimated position x hat t plus 1, the next position x hat t plus 2 is further estimated. So by repeating the calculation, the future positions of the target are gradually estimated. Finally, the target reaches a candidate cell here, for example. So a series of the position is the estimated future positions of the target x hat t. Moreover, when the estimated future position of the target reaches a candidate cell, this cell here is the estimated destination. In terms of surveillance, searchers are required to take into account not only a monitoring spot, but also a series of actions toward the spot. This is the optimal approach behavior of searchers in this presentation. So we have actually just proposed an optimal patrolling strategy for mobile robots. A value iteration method has been used for calculating an optimal action in every state. Okay, the output of this method was so-called a state action map. The space of the environment is already divided into the cells, so we also focus on this state action map in this research work. So in the value iteration method, first off, the state is defined as a cell occupied by a researcher, and the action is defined as a moving direction of the searcher in the cell. The optimal action indicating the moving direction in each cell is given to the searchers as a policy. Okay, so for calculating the policy, we first off use the following value function here, V. By repeating the recursive calculation of the value function, finally, the state value is optimized on the basis of Bellman update. For the optimal value function V star, an optimal action in each state is obtained with the use of greedy algorithm. The optimal action in state S is represented by pi star S. This policy pi star is used by the searchers as the state action map. Consequently, the searchers are enabled to move toward a cell with the maximum value of V star according to the moving direction, which is pi star. A series of the actions is the optimal approach behavior of the searchers toward the target. Okay, and in order to have this optimal policy pi star, we have to design the reward function, as you can see here. So we present two reward functions. And this is the first reward function where Pi is defined by the moving probability of a cell and the maximum moving probability. And dp max and dd are normalized distance by m, and these are the distance between cell I and the maximum cell with and the cell with the maximum moving probability and estimated destination cell. Here, m is a diameter of the monitoring area. The reward function enables the searchers to proactively approach the target in consideration of the moving probability and destination. In addition to this reward function, we further take into account an encounter area between the searcher and target, as you can see here in this figure. In consideration of the counter areas, we designed the following reward function. Here, the alpha is pretty much important factor, which is given 1 if cell I is in the encounter area, and 0 in other cases. So this reward function enables the searchers to approach the target in consideration of the encounter area in addition to the moving probability and destination. Okay, so in this simulation experiment, we first focus on the estimation accuracy for the future positions of the moving target. So for each of two moving targets, two destinations and the straight and the curve paths are given, as you can see here, this one and this one, right? And for comparison purpose, the destinations are estimated with the use of a linear path that passes through the recently monitored positions, xt and xt-1. For the estimation, the moving probabilities were calculated in advance. So as you can see here, the cells along the path here and here have higher blue probabilities. And this table shows the average destination gap between the estimated destination and the true destination in each step. As for path 1, the estimation gap was about 30 meters. Okay, in consideration of the size of a cell, which is 20 kilometers, both the methods successfully estimated the correct destination. On the other hand, as for path 2, the proposed method estimated the destination with the 7-fold greater accuracy than the comparison method. This is because that, as you can see here in this figure, the target continuously changed the moving direction rightward. Okay. Based on the estimation, the searchers approached the target in this surveillance system. In total, 1,000 targets come into the monitoring area. Each of the target is given a random waypoint and destination. And the 3 searchers move at the velocity of 300 km per hour, and the target moves at a velocity of 600 km per hour. For aerial surveillance, the following 5 strategies are applied to the searchers. The first strategy allows the searcher to approach the current position of the target. The second strategy allows the searchers to approach the estimated destination. And the third strategy allows the searcher to approach the cell with the maximum moving probability. And the fourth and fifth optimal strategies are based on the designed reward functions. The fifth optimal 2 strategy is based on the reward function in consideration of the encounter area. As shown in this figure, when the target is in the red sensing range of the searcher identifies the target. So we first compare the performance based on the first, second, and third strategy. So this table shows the number of identified targets. So compared to the first strategy, the searchers based on the second and third strategies identified more targets. So this result indicates the effectiveness of estimating the future positions of the target. The third strategy resulted in the best performance from the 3 strategies. So the result of this strategy is compared to the fourth and fifth strategies as shown in the following table here. And compared to the third strategy, the searchers based on the fourth and fifth strategies identified more targets. So this result indicates the effectiveness of the optimizing a series of the actions of the searchers. Moreover, although the fourth and fifth strategies were optimal, the number of identified targets based on the fifth strategy was increased by approximately 100 compared to the fourth strategy. So this result indicates the effectiveness of taking the encounter area into account. In other words, the searchers successfully identified the most target by ignoring the cells outside the encounter area. In order to observe the optimal approach behavior of the searchers, we compare the trajectories. These figures show the result. In this figure, we can see that the searchers failed to identify the target, as you can see here. On the other hand, in this figure, the target was identified by the red searcher, as you can see here. This is because that the red searchers moved almost in the same direction as the target. So this behavior successfully enabled the searcher to approach and identify the target. Okay, that's it. Thank you for your kind attention.